Alright guys, we are going to do a simple example of some vector addition here. This example is not anywhere in your notes packet, so you'll just have to bear with me. I was going to do microcoulombs, but there's no symbol for micro that I can do in Explain Everything, so it's going to be nanocoulombs for everything. Alright, the charges here, we're going to be figuring out the net force that they are exerting on that other one over there, the 2 nanocoulombs. So if you recall from class, where we start was find the net force by drawing arrows. You got to start with some kind of a diagram. Okay, so that's where we're going to start, is by drawing a diagram of the forces. The 3 nanocoulomb and the 2 nanocoulomb are going to be repulsive because they're both positive. So that force I'm going to indicate in blue is going to be something like that. Okay, there we go. Let's call that one F1 for no particular reason. All right, the other force between the negative 3 nanocoulomb and the positive 2 nanocoulomb is going to be attractive, and therefore towards the minus 3 nanocoulomb, and that we're going to call F2. If you recall from class, we said that the force is going to be KQQ over R squared, R hat, where the KQQ over R squared part is the magnitude and the R hat is the direction. The magnitude for, let's say, F1 is going to be K times the 3 nanocoulomb times the 2 nanocoulomb over distance between them. Oh my goodness, it's not given in the diagram. Well, it says this distance is 1 meter, this distance is 2 meters. So do not panic. We can use a little bit of Pythagorean Theorem, and we can figure out that, hey, that distance right there is going to be the square root of 5 meters. And ditto for this distance, right? That's also going to be the square root of 5. Okay, so if I square the square root of 5, guess what? That's going to be 5. That's some terrible penmanship right there. Let's try that again. That's supposed to be a 5 down there or something. That's better. Okay. Now, the nano part here, I was being sloppy because I didn't feel like writing out times 10 to the negative 9th and Explain Everything. So I guess you could say I cut a few corners there. But let me pause the video for a moment, and I'll calculate a magnitude, and you can do the same. So we get that magnitude is F1 equals 1.08 times 10 to the negative 9th newtons. Okay, and if that's all that we wanted to know, then that would be pretty straightforward. But since we're trying to add F1 and F2 together, we're going to need to do a little bit more. This is where the vector addition part comes in. All right, now, if you went ahead and you plugged in the same numbers and everything for F2, it's the same numbers. So we're going to get that F2 is the same thing, except that the directions are, as you can see from the diagram that we drew, a little bit different. Okay, not exactly opposite, right? But we're going to have to take into account those directions somewhere, and that's where the R hat part comes in. Okay, so if I added together F1 and F2, I can actually simplify my work a little bit. I don't have to calculate everything so painstakingly. I should be able to just say, well, based on what I'm seeing here, since F1 is basically to the right and F2 is basically to the left in terms of I components, and since they're of equal magnitude and in the same direction, the I components will cancel. So if I do F1 plus F2, because the magnitudes of those two forces are the same and because their I components are in opposite directions, I can say that the I components will just cancel. So when I get F1 plus F2, it's going to be more or less 2 times the j component of each one. Okay, let's think about that a little bit more. All right, so what we're saying is i's cancel, j's add. Okay, let me pause for a moment, give you a little bit of time to think about that, and then I'm going to erase some of that text so that I've got enough space left to write. So again, the i's are going to cancel, the j's are going to add. I'm going to make some of this text disappear. So I'll just leave on the F1 equals, have a magnitude for it, and then we'll start figuring out, okay, what are the j components and such. All right, there it is, transition. We have F1 and F2, cosine theta, okay. And what we're trying to express here is that the two forces are equal in magnitude, that's these bits, and then here's the r hat for each one. Now what I haven't done is supplied things like sines, so I'm going to add those in, and then we'll start coming up with exactly what cosine theta and sine equal, like given that there's no angles labeled and stuff, which actually is not going to be a problem. All right, for F1, the I component is in the positive I direction. The j component's in the negative direction. I'll go ahead and slop a negative sign in there. There it is. All right, for F2, the I component is in the negative direction. The j component is also in the negative direction. Okay, so what you should see then is these two parts are going to cancel. Right, because the two forces are equal in magnitude, but the I components are in opposite directions, so I'm not even going to worry about what cosine theta is, because they're just going to cancel. All right, so when all is said and done, our final answer is just going to be the two j components added together. So here's what it will be. It will be 2 times 2 because we're adding the two forces together, and it's going to be whatever 1.08 times 10 to the negative 9th sine theta j is, plus the same exact thing. So 2 times that. So 2 times 1.08 times 10 to the negative 9th. Whoa. Sine theta j. All right, so that's what it's going to be. All right, now let's break this last part on down. Some of the things I wrote in there disappeared. I had my whole root 5 thing going on. Let's add that back in. Because we're going to need that when we figure out, okay, what is sine theta anyway? All right, back to basic trigonometry, y'all. Sine theta is, y'all remember SOHCAHTOA. It was opposite over hypotenuse. All right, and then cosine theta, which in this case we don't really need, but I'll mention it anyways. It's adjacent over hypotenuse. Adjacent over hypotenuse. Let's try that again. Adjacent over hypotenuse. All right, and remember we said we're always going to define theta as being like from the horizontal. So for my particular diagram here, I'm going to define theta as being, say, this angle there. Okay, it could just as easily be this angle here, that's the same angle, or that angle, again, that's the same angle. They're all the same angle, right? So we just need to know, all right, what is sine of that angle? You don't need to know what the angle is equal to. You honestly don't. Okay, you could go through a lot of trouble to figure out the angle and then like use inverse tangent and then take the sine of that and then get a number. But that's not really going to help you very much for like a symbolic problem, which this one isn't, but that would be a more complicated way to do it. What we have is, if this is our angle, right, there it is, if that's our angle, the opposite side to that angle is 1 meter. The adjacent side is the root 5. That means that opposite over hypotenuse is going to be 1 over root 5. All right, if we had to do cosine, cosine is adjacent over hypotenuse. This adjacent side here is labeled as 2 meters, right? That right there, that's 2 meters. So cosine theta would be adjacent is 2 over the hypotenuse is root 5. Okay? All right, so again, we didn't need to actually figure out what the angle was. You could if you wanted to, but it doesn't matter. Sine theta is the ratio of the opposite and the hypotenuse. That's what it is. So if you know that the opposite is 1 and the hypotenuse is root 5, then sine of whatever the angle is going to be 1 over root 5. Okay, so our final answer will be 2 times 1.08 times 10 to the negative 9th times 1 over root 5, which is a number. I don't really care what that number is, okay, but that right there is going to be our final answer. Don't forget the j hat, because we're saying that total force is in the downwards direction, so I guess we really actually negative sign in front of it. Okay? There it is. All right, obviously this is the internet, so if you need to see any part of this again, just back it up and watch it again. All right, I hope that helps. Thanks very much.